This video is a continuation of the notes from section 1.4. We did one of everything in class, but I said that I would go back through and work through the extra examples that were similar. Sorry, so see section 1.4, not section 1.3. And we were on example 3, part D. We're trying to add these fractions together that possibly may have a common denominator. The first thing we'll want to do is factor all the denominators to see what that common denominator might be. So this is a trinomial, so factors of 9, and it leads with a 1. So we just need factors of 9 that add to 6. So that would be a positive 3 and another positive 3. And then this would be two perfect squares, so that would be an x plus 3 and an x minus 3. And then we have an x minus 3. Now, typically, our LCD we just find by looking at only the denominator because we just factor it and we say, okay, what is the common factor? We see an x minus 3 and an x plus 3 in this denominator, which this one also has an x minus 3, so that kind of matches with that. But we do see two x plus 3s in this denominator. Now, typically that means that we would need an x plus 3 squared because there are two of them in the same denominator as our LCD. But I want to point out that you should always check the top if you have something squared like this to see if it could be reduced out. And if we pull a 2 out of that top, we can actually, because this is in the same fraction together, we can reduce that out. So I'm going to rewrite this as this is now 2 over just x plus 3. That's the reduced fraction for this, plus 5x over x plus 3, x minus 3, plus 7 over x minus 3. Okay, so my next step would be to say that my LCD is now just an x plus 3 and an x minus 3. I don't need two x plus 3s since I was able to reduce one of these out. So we ask, what is each fraction missing? Well, the 2 over x plus 3 needs the x minus 3. So what we do is we multiply the bottom by x minus 3 to create the denominator. But whatever we do to the bottom of a fraction, we also have to do it to the top to stay consistent, and we're really multiplying by a big 1. The middle fraction already has the desired denominator, so we don't need to make any changes there. The final fraction has an x minus 3, but it needs an x plus 3. So now what I have is that I have one big fraction, and the denominator is x plus 3, x minus 3. On top, we're going to write this out. This is 2 parentheses x minus 3 plus 5x plus 7 times x plus 3. You want to work out the top completely. Do not cancel anything at this stage. There's all this addition connecting everything. So this would be 2x minus 6 plus 5x, and this would be 7x plus 21, all over x plus 3, x minus 3. We add our like terms on top, so 2x plus 5x is 7x. 7 plus 7 would be 14x. And then negative 6 and 21 would be positive 15. Now, notice that the top is a binomial, but there's no GCF. It's not perfect squares or perfect cubes, and it has nothing in common with the binomials on the bottom. It's not identical to them. So that is our reduced final answer. Okay, we did A part for the complex fraction, so we're going to start with B. For B, we can choose either one of two methods. So I'm going to show you both methods again. Method 1 is that you get a fraction on top and a fraction on bottom by combining those things by getting common denominators, and then you multiply by the reciprocal of the bottom. Method 2 is that you clear the fractions that are little out right away by using a big LCD for the whole problem. So for method 1, which is we want to do one fraction on top over one fraction. That's kind of the goal. And then we multiply, sorry, let me give a little space between that. So one fraction over one fraction, and then we multiply by the reciprocal. So that's kind of our process. So the first thing you want to do if you're doing method 1 is you want to get a common denominator on top. So it looks like the top fraction, we need to write it as they both need each other as their denominator. So the first fraction needs an r on the bottom, so we'll multiply it by r on top and bottom. The second fraction needs an s on the bottom to match the first one, so we'll multiply top and bottom by s. That's going to make that r squared plus s squared over rs. So that's my now new numerator once I combine those like fraction or common denominators and get something we can add together. For this one, we need r squared and s squared to be our common denominator on bottom because you need both. So we're going to multiply the first one by r squared over r squared and the second one by s squared over s squared. And that's going to equal r to the fourth on the first numerator minus s squared times s squared is s to the fourth, and that's over r squared s squared. So once you have a common fraction, one fraction on top, one fraction on bottom, you change this to multiplying the first fraction by the reciprocal of the second fraction. That's where this division symbol right here in the middle turns into times. And then we have to ask, does anything reduce? Well, the r and the s can reduce with one of the r's and one of the s's here since there's no plussing or minusing. So this becomes a 1, and this would just become an r and an s. It would reduce one of those each. This doesn't actually match this, but this is factorable. R to the fourth and s to the fourth are both perfect squares. The square root of them would be r squared and s squared. So this actually factors into r squared plus s squared and r squared minus s squared. So what that means is that the r plus s squareds can cancel out. So my final answer is rs over r squared minus s squared, or you could even factor this again and say it's just rs over r plus s, r minus s, using perfect squares again. So I prefer the completely factored method, but that's just me. This would also be acceptable. So that's using method 1. Method 2, which I'm going to work kind of over here to the side. For method 2, you try to clear out the fractions by finding a common LCD for everything on top and bottom. So you look at all the little fractions, s, r, s squared, and r squared. To get rid of all of them in one step, you need the bigger power of each, so r squared and s squared. To use this method, you take each fraction and you multiply it by r squared, s squared. Now notice this is kind of like over 1. So you do this to everything on top and everything on bottom. So there's the top. So times r squared, s squared, and then the bottom is s squared over r squared times r squared, s squared over 1. If you've picked the correct LCD, all the little fractions should cancel out. So this s cancels with one of those. So this is r times r squared, which would be r to the third, times that one s that's left over. And then one of these r's cancels with one of these, and you have s times s squared is s cubed, so plus s cubed. And then we have that r over. On the bottom here, the s squareds cancel, so you just get r squared times r squared, which is r to the fourth. On the second one, r squareds cancel, and you get s squared times s squared, so that's negative s to the fourth. Now you're thinking that doesn't look like the final answer we got on the other version, and they should be exactly the same if we've done this correctly. But you haven't factored this yet. You can pull out an r and an s on the top, so that would make that rs times r squared plus s squared. On the bottom, this is two perfect squares again, so it's r squared plus s squared times r squared minus s squared. And there's where that cancels, and we get the same answer again. So it does work out. One of them is usually easier than the other, method 1 versus method 2, but like I said, you don't want to try to learn both. You really, in this class, every problem we give you, you'll be able to do either one. So it's better just to focus on the method that you like best. Now, I always throw out C. It's not in the homework. It's not on the quiz. It's not on the test. I just need to remove it from my notes, but it is not on there. So we're just going to skip that one. And then the very last example is another example of the big factoring problem. The only thing that makes this one a slight difference than the one we did in class is that this is a negative exponent. So on one of our factors, there's a negative exponent. That means at the end, we'll have to move that to the bottom of our answer. So the first step again is to kind of locate your plus sign in that middle so you see the separation between the two pieces, the two blobs. So then this, I always clean up my monomials first. So 2 times 4 would be 8. Then I have my 3x plus 2 to the negative 4 times my 4x minus 5 to the first. On this side, I have a negative 2 and a 3 that are both monomials. So I get a negative 6. And then I still have a 3x plus 2, but this time it's to the negative 3, and a 4x minus 5 to the second. Once you have figured out how to simplify the monomials down, you then look for a large GCF to pull out. Now, 8 and negative 6 are both divisible by 2, so we can pull out a 2. Most people have an easier time with the 4x minus 5. Since they have 1 in common, we can pull out a 4x minus 5. So I'll go ahead and write that down. When it comes to the 3x plus 2 and you have these negative exponents, notice that when we had a 1 and a 2, we ended up picking the 1, the smaller number. That's because you always have the smaller amount of things in common. The same thing works for negative exponents. People just have a hard time with what is a smaller number as a negative exponent. Negative 4 is actually smaller than negative 3. So we're going to pull out 3x plus 2 to the negative 4. So we're going to talk about what's left in each of those blobs up here. So 8 divided by 2 would be a 4. We pulled out all of those, and we pulled out all of that. So actually, that's the only thing left in the first part. Negative 6 divided by 2 would be a negative 3. Now, here's a problem that most people have with the negative exponents. You pulled out negative 4, right? Here you have negative 3. We have pulled out, so when you pull something out, you're dividing. So you're doing 3x plus 2 to the negative 3 divided by 3x plus 2 to the negative 4. So anytime you're pulling something out, you're taking what you had and you're dividing it by the GCF. These are same base, so you're just subtracting those powers. So negative 3 minus negative 4 is actually plus plus. This leaves you a positive exponent. That's why we always pull out the smaller one. So this will just be a 3x plus 2 to the first, and this will also be a 4x minus 5 to the first because we pulled out 1. So the final steps usually are to clean up this big bracket part, and then we will need to make sure our exponent is positive at the end. So let's try to finish this. So I'm going to do some scratch work right here. This would be 4. Distribute that. That would be, oh wait, no, don't distribute the negative 3 yet. You have 2 binomials. Let's FOIL this out first. So I'm going to have a plus negative 3. This is all about order of operations. Some people try to add these together first. That's not legal. You have to multiply everything out before you can add that 4 at the end. So usually when we multiply, we do the more complex parts first. So this will be negative 3 times 3x times 4x is 12x squared. 3x times negative 5 is negative 15x. 2 times 4x is positive 8x. 2 times negative 5 is negative 10. Now we're going to distribute this negative 3. So that's going to be negative 36x squared. Negative times negative would be positive, and 3 times 15 is 45x. Negative 3 times 8x would be negative 24x. Need to give my computer a second to catch up. And negative 3 times negative 10 is positive 30. Now we can combine all of our like terms. So this is becoming 2 parentheses 3x plus 2 to the negative 4 times 4x minus 5 times negative 36x squared is the only x squared term. 45 minus 24 would be 21. So positive 21x. And 4 plus 30 would be positive 34. Now, I've already checked that doesn't factor again. The only thing about getting your final answer is that that negative exponent right there needs to have the base it's attached to, remember, move to the bottom. So it actually ends up being 2, 4x minus 5, and then the big trinomial, all over the part that had the negative exponent, which once it moves, it'll be a positive exponent. And that's the final format that we want to leave it in. So this truly is, it's complicated looking, but there's really nothing going on here but pulling out GCFs, distributive and foiling properties essentially, and adding like terms. So there's not much here that's truly difficult if you know what you're supposed to do. And that's the end of the 1.4 extra examples.